Hi again. What I did until now, I just made some summary for you so that you wouldn't wait for the video while you're listening my writing. So it's written already. Now, in this chapter, we have lots of actually calculations and lots of comparing and hypothesis testing. So I will try to summarize them. Now here, at the beginning of the chapter, we have statistical inference for a single sample. So we think that there's a population, and from that population, we choose random sample. What can we do with this sample? There are two alternatives. One is we can estimate the parameters. What are the parameters? The mean of the population and the variance of the population. So we will estimate them from the sample. And this can be point estimation. Point estimation just says that whatever you find as an average for the sample is the point estimation of the population mean. And what you found from the sample as a variance is the point estimation of the variance of the population. But in general, we are not happy with this point estimation, and we would like to know the confidence interval for the estimations, because we want to know what percentage we can make a mistake. Let's say that we found from the sample that the average is 2, but let's say that the real average is 3. If we make a point estimation, then we just say that the population average is 2, but it would be wrong. In confidence interval, we would just give some kind of an interval so that we will say that, for example, 95% we are confident that the average is between these numbers, whatever these numbers are. So we will say that we are 95% confident that the average is between these numbers. So this gives us the range for the mean of the population. The second evaluation is an hypothesis testing. We can say that we are estimating the population average as null hypothesis, let's say 2, and we will say that as an alternative hypothesis it is not equal to 2. So when we make hypothesis testing, it can be one-sided or two-sided. We will go in depth about these terms. We will either accept the null hypothesis or we will reject it and say that the average is not equal to 2. So we have two different ways of using the information we get from the sample. Now let's look at hypothesis testing. For this testing, we have a null hypothesis. For example, until that time, we are producing that item, and we're always measuring it as 10 centimeters, for example. So we can check whether the average is still 10 centimeters or not, and we may write an alternative hypothesis for this one. If what we found from the sample is just away from the target, the target is just in the middle, so away from the target, we can reject the null hypothesis, saying that the average is not 2 anymore, for example. It is found from the sample. So one-sided means we only check, we only have a lower limit for this one, and we have a upper limit for this one. For two-sided, we put limits for both sides, lower and upper limits. The important difference between one-sided and two-sided is that we have an alpha value. This alpha value is actually, we wrote here, is rejecting null hypothesis. Sorry, let me show this here. Rejecting null hypothesis when when H0 is true. So since this is the distribution of the population, there is a possibility that we have chosen sample from here. If we chose from here, it means that the sample doesn't actually represent all the population, but there's the possibility of choosing from this area. We could have chosen sample from here, and this is actually the reject area of the null hypothesis. So we name it as alpha, and from one-sided we only put alpha for here. But for two-sided we need to divide alpha by 2, because when we add both sides it should be equal to alpha. So these are the rejection regions. This is very important in calculations. For one-sided we will take alpha for calculation, and for this one we need to divide alpha by 2. Now, what is the meaning of alpha? And we have beta and there is power. So what is alpha? Alpha is type 1 error. So what does that mean? Although we are producing at the target, we may choose from this area so that we may conclude that the population average has changed. So that's a mistake. That's a type 1 error. And it is rejecting the null hypothesis, although null hypothesis is true. There's a beta, and that's the probability of type 2 error. What is type 2 error? It is failed to reject the null hypothesis, although the average of the population has changed. We can select from the area so that we conclude that it didn't change. Let me try to explain this to you. Now, this was the previous distribution of the population, and this was mu, let's say mu 0, and by time the distribution has moved from some kind of a reason, but we don't know. As engineers and in quality, we would like to catch this moment, this change. So there's a rejection point, rejection area, this area. Now, let's say that the production average has moved to right. And since we reject from here, of course the selection of sample from here is high, but there is a possibility that we have chosen sample from this area. So sample may be chosen from here. So it means that if we take a sample from the not rejecting for part, we may conclude that although the average of the population has changed, has moved, since we select a random sample from the accepting area, we may make a beta error, which is type 2 error. What does that error say? Fail to reject although the null hypothesis is false. This is false, you know, because it is moved to, let's say, mu1. But we couldn't catch this. We couldn't catch this movement since we selected from this area, and we concluded that the average didn't change. That's a mistake. That's a type 2 error. So let's go on with our subject. Type 2 error, we said. And there is power, and power is actually the power of the hypothesis testing, and we can calculate the power by subtracting beta from 1. So what is the meaning of power? Rejecting null hypothesis when null hypothesis is false. So it means that rejecting, you know that this part was the rejection area. So beta, since this was beta, you know, selecting from the accepting area. So this shaded, blue shaded part is 1 minus beta, and which is power. So power means catching the change in the production. And we also name these alpha and beta values. Alpha is producer's risk. Why? Because since the production has not changed, let's say this is our production and we produce at the target, but we have some rejection areas, and randomly we have selected from this area, and as a conclusion we said that the production is not at the target. So that's a alpha producers risk. Although the producer is producing at the target, since there is a sample selection from the rejection area, the company said you're not producing at the target. So that's the producer risk. And for this one, although the producer's average has moved, since we select from the acceptance area, this means that our quality has changed. If our customer wants an average of mu0, we are now, as a producer, producing at mu1, and the customer doesn't catch this. So that's the customer's or consumer's risk. Beta is the consumer's risk. So confidence intervals, how do we calculate the confidence intervals? When it is two-sided, we say that we have an upper limit, we have a lower limit. What is the probability of being having a mean between these specifications is 1 minus alpha. And by saying this, what do we say? This is very important, actually. This part is very important. We always give producer's risk as a rejection part. If it is two-sided, like here, then it's divided by 2, 0.025 is this part, 0.025 is that part, and as we add it, it is 0.05 as the alpha value. This is called 1 minus alpha alpha may be 0.05, and this is 95% confidence interval. So we will decide on alpha. Now, what are the values an alpha can take? Generally, alpha is 0.05, but if you're producing a very important thing like medicine, this can be lowered to 0.01 because it's very important for consumers' health. So you can want to be 99% confidence interval. So it changes according to the consumer and the producer's risk. So confidence bound. Now, what is the difference between the confidence interval and confidence bound? Confidence interval, as a word, it means between some numbers, between. But confidence bound means either you have a lower bound or you have an upper bound, so it means one-sided. A one-sided lower, again alpha, 100 times 1 minus alpha percent, confidence bound on mu average would be shown like this, and it will be 1 minus alpha. Again, the other part, 1 minus alpha. As we solve the problems, we will try to see the differences between the two-sided and one-sided calculations. So let's look at the hypothesis. How do we form the hypothesis? Now we write H0 as the null hypothesis and H1 is the alternative hypothesis. For example, the null hypothesis may be mu is equal to 1500 and the alternative hypothesis will be mu is not equal to 1500. Again, we have alpha, beta, and power. So inference on the mean of a population. How do we calculate when the variance is known? How do we inference on the mean of a population? We write the hypothesis testing. H0, mu is equal to mu 0. And alternative one is H1, mu is not equal to mu 0. So we need to calculate the z-value in order to either reject or accept the hypothesis. And our formula for this one is like this. Z0 equals x bar. X bar, you know, is calculated from the sample average, and mu 0 is actually testing value. This can be the population average, which has recorded before during so many productions. So you want to check whether this mu 0 has changed or not. If it is changed, then it means that there's a problem in the production. So you need to take care of the production. So maybe let's say for 2 years you have produced at 2 centimeters something. You should put it here. And sigma, since the variance known, we know the variance of the population in this case. When do we know the variance of the population? When we are producing for a long time, the variance becomes a standard. Let's say 1.5. We always produce at 1.5. But of course, companies would like to lower this variance because lowering the variance means you're hiring your quality. You're improving your quality. So sigma, when it is known, it means that you are producing for a long time and it is almost standard for the production. And we divide sigma by the square root of how many numbers we take as a sample. Confidence interval on the mean with variance known when two-sided. You know what when two-sided is, when we draw the graph, when we have limits from both sides, this equation is used. So what's this equation? X bar, this is the average from the sample, minus z alpha over 2 because we divide by 2 since it's both sides. This is alpha over 2 and this is alpha over 2. We calculate this value from the table. Sigma, since we know the variance, this is the almost standard variance, and that's the square root of n. So this is the lower limit and this is the upper limit of calculation. And we have confidence bound on mu. We have only a upper limit in this one, and we have only lower limit for this one. If we want to draw the graphs for these, this will be, this would have an upper bound and this would be alpha, and for this one we will have a lower bound and that part would be alpha. So in calculations we need to be careful about when do we take alpha over 2 and when do we take alpha as the calculation value. Let's look at example 4.2. It says the expected value of mu is equal to x bar, and that's 79.25 milliseconds. Find the 95% two-sided confidence interval. When it is two-sided, you know, we will use this formula, and we wrote the same formula here. Now we put 79.25 in place of x bar because it is the average of the sample. We found this 1.96 from the table. Let's look at the table. Try to read the table. What was alpha? Alpha was 0.05. But since it is both sides, we need to divide 0.05 into 2, and that will be 0.025. So we will try to find 0.9725 here. 97.25, it's here. So 1.9025 0.025. Oh, no, not this one. Okay, we will go on. We are looking for 975. 975 would be here. It is just exactly 0.975, and we look at the z value here, 1.9, and we go up the column and it is 0.06. So it means 1.96 is the z value when we have alpha over 2 0.025. So here's how we found 1.96. Then 8 is the sigma for this case. sigma was 8 in the previous example. So all over 25, n was 25. And we calculate, when we calculate this, it is 76.114 is less than or equal to mu, less than or equal to 82.386. Now, how do we interpret, or how do we say when we look at this results? Our estimate of mean response time is 79.25 milliseconds plus minus 3.136. So this is what is written here, and plus 3.136 and minus 3.136 with 95% confidence. So that's the evaluation of these results. Now we can also use p-values for hypothesis testing. I mean, without calculating these results, we can find the p-value and compare this p-value with our alpha value. If this p-value is less than our alpha value, what does that mean? Let's say that it is one-sided and it is alpha. If we found that our p-value is, let's say alpha is 0.05 and our p-value is 0.01, which is at the very right part, which is also at the rejection part, then we say that we reject the null hypothesis. So what does it say? Alpha value is the level of significance. P-value is the smallest level of significance that would lead to rejection of the null hypothesis. So let's write it. If p-value is less than alpha value, then the null hypothesis is rejected. You can either remember this, or you can either draw a graph like this, shade the alpha value and shade the p-value, then you would see that p-value is at the rejection part of the alpha. So in example 4.1, the z-value was 2.66. The alternative hypothesis was one-tailed, and p-value, as we calculate from the z-value, was 0.0039. Now, where is it? If our alpha value is 0.01, then our alpha value should be like here, because it's greater than this. So p-value is at the rejection part. This is greater. So this area is greater than this area. Since alpha value, as we said before, since alpha value is greater than p-value, H0 would be rejected. We rejected null hypothesis. Let's draw it again if you would wish. So for this side, we said that alpha is equal to 0.01. And by calculation, we found that our p-value is 0.0039. So it is far away from the target, which says that mu is equal to mu 0. But since we have selected from this area and it is just very far away from the target, also it is at the rejection area, rejection of null hypothesis area, we reject the null hypothesis saying that mu is still equals mu 0. There should be some change. We are expecting some kind of a change that we have found this as the average.